Hello dear friends, today I want to discuss general relativity energy momentum tensor part 2. So friends, let's discuss this topic. So component of energy momentum tensor T alpha beta flux of alpha momentum going through a unit box of constant beta, and T alpha beta equals to amount of alpha momentum going through a 3D unit volume of constant beta. So friends, before these discussions part 1, I have I have been discussing number flux. So friends, number flux we used for the number flux four vectors, except 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 this time we are going to be continuing four momentum inside of a box instead of just the number of particles inside the box. So friends, I have drawn some particle. Now I discuss 1D unit length. Let's go back to our 2D space-time diagram. So friends, this is a 2D space-time diagram, ET and EX, and time and x with particles moving in the positive as their own four momentum vector that they are carrying with per unit length delta x. So inside this unit length at constant time, all of these four momentum vectors have a time component and x component. If we look at the time component, this gives us the time component of the energy momentum tensors. This is total time momentum crossing a boundary. So friends, box del x, you can see this diagram del x, box del x of size 1 at constant time ct. Total time momentum tt, total time momentum is equals to t, and total x momentum equals to t xt. Constant time we also look at the total x momentum in this unit length. This gives us x time component of the energy momentum tensor, which is the total x momentum crossing a boundary of constant time. Now 1D p flux per unit time, box del ct of size 1 at constant time x such that total time momentum is equal to t, and total x momentum equals to t x. We can also look at the total momentum contained in the x flux of particles, which is just particles that pass through some point at a constant x value in 1 unit of time, which is represented by a vertical. So friends, now we will say that energy momentum tensor is C may so T alpha beta equals to T beta alpha. We can see this in our space-time diagram geometrically. The amount of x momentum coming out of the surface of constant time, the xt component is equal to the amount of time momentum coming out of the surface of constant x, the dx component. Here you get t x t and t x, and after that in this diagram you see that t xt equals to t tx. Generalized to 4D space time, capital T alpha beta equals to amount of alpha momentum going through 3D unit volume of constant beta. Instead, if we take a xyz box, so friends, we take xyz box. This is the unit del z, this is the unit del x, and this is the unit del y. If we take an xyz box of unit volume at some constant time, then time is, friends, constant t alpha t. Here time is constant. So friends, whatever we see, we will see pt divided by del x, del y and del z equals to capital T divided by del x, del y, del z x equals to t x t p y divided by del x, del y, del z equals to t y t p z divided by del x, del y, del z equals to t z t. So friends, here t is constant. We can count up the total time momentum, x momentum, y momentum and z momentum. This gives the pt, xt, yt and zt components of the energy momentum tensor. We could also take a unit box made of time y and z with a constant x component to examine the flux of 4 momentum in the x direction, this would be the alpha x components of the energy momentum tensors, since the x coordinate is held constant. So x coordinate constant t alpha x. So here x is constant, portion is constant, pt divided by del ct del y del z equals to t p divided by del ct del y divided by del z equals to t x del ct py del ct del y del z equal to t y p z divided by del ct del y del z t z x. We look inside the box and calculate the total time x, y and z momentum. This gives us tx, xx, yx and zx components of the energy momentum tensors. We can use a unit time xz box at constant y to get the alpha y components. T alpha y, where p t divided by del ct del x into del z equals to t capital T y, and px divided by del ct into del x into del z equal to tx. Sorry, here y is constant, so xy py divided by del ct del x into del z equals to pyy. Similarly, pz divided by del x into del z divided by tzy, and a unit time xy box at constant z t alpha z, where xy box, this is the z is constant, and del x del y and del ct is the unit box. So t alpha z equals to pt divided by del ct del x del y equals to tt z pt px divided by del ct del x del y equals to txz pt divided by del ct into del x into del y equals to, sorry, it is not pt, it is pyz. Pz divided by del ct into del y equals to tzz. So friends, energy momentum tensor equals to is a matrix representation t tt t y t tz t xt t xx t xy t xz t yt t yx T Y Y, T Y Z, T Z T, T Z Y, T Z Z. So T T T T T T T T T T T T X T T Y T Z X T X X X Y X Z Y T Y X Y Y Y Z Z to Z X Z Z Y Z Z. So this is our energy momentum tensor. Energy momentum tensor show these 16 components and gives us the full description of how full momentum is moving through space-time, a bunch of particles moving through space-time. Space-time will each have their own world line. We will each have their own world line. The result is like a river of full momentum which looks like a little bit like spaghetti. Like spaghetti. If we take a cross section of the spaghetti using a unit box at constant coordinate, then the total force momentum in this box will give us of 16 components. You see this diagram, this is the spaghetti. This diagram is spaghetti. We consider a unit box. This box is unit box. Then T alpha beta equals to flux of alpha momentum. T alpha beta is equal to flux of alpha momentum going through a 3D unit volume of constant beta. Energy momentum tensor T equals to machine that take two unit vectors input. Machine two unit vector inputs and outputs the A momentum in V direction. Momentum in V direction inside in 3D space-time box perpendicular to W vector. So momentum in V direction inside A in 3D space-time box. 3D space-time box and perpendicular to W vector. If we see this diagram, then if V direction is V direction is this is V direction and this is direction perpendicular to W, V in W, and therefore T alpha beta can be written equals to T E alpha E beta. We get when the momentum direction is a basis vector E alpha and the 3D space-time box is denoted by a perpendicular basis vector E beta. T alpha beta amount of alpha momentum going through T alpha beta equals to amount of alpha momentum going to 3D unit through a 3D unit volume of constant. So our tensors is T alpha beta can be written T alpha beta equals to, so friends, T alpha beta is equal to TT, TTT, TTX, TTY, TTZ, TXT, TXX, TXY, TXZ, TYT, TYX, and TYY, TYZ, and TZT, TZX, TZY, TZZ. We can think of alpha beta components of the energy momentum tensor as the flux of alpha momentum crossing a unit volume of constant beta. We should remember that the time component of full momentum is the energy of a particle. So the first row of the energy momentum tensor, where alpha is the time index, is really about the energy of particles. Also the phrase flux across a volume of constant time is really just a word density across space, which is the amount of stops in a xyz unit box at a constant time. So the first column, where the beta is the time index, is really about densities across space. This is T momentum energy. This portion is T flux spatial density. T flux spatial density. We should remember that the time components of force momentum is the energy of particle. So the first row of energy momentum tensor, where alpha is the time index, is really about the energy of the particles. Now this portion TTT portion is called energy density, and this three portion is called pressure. As momentum as Txx is equal to Px divided by del T into del Y into del Z equals to Fx divided by del Y into del Z, and momentum divided by time equals to force, and force per area equals to pressure. So friends, you know that this push with coordinate Cartesian coordinate del E mu divided by del x gamma equals to 0. That implies gamma sigma mu nu equals to 0. We are working in special relativity in standard Cartesian coordinates. The connection coefficients in our derivatives first portion is divergence. Let's take the component in the top row of the energy momentum tensor. Top row of the energy momentum tensor, this is the top row. This tell us the flux of the time component of momentum on energy through various boxes in each coordinate directions. Divergence. So let's take TTT, TTX, TTY, and TTZ. Let's take the divergence of this component, so we differentiate the four components. Del TT divided by del CT, del TX divided by del X plus del TY divided by del Y plus del TZ divided by del Z. This divergence, this portion. Now del TT for rho, we can say del rho energy, this portion energy divided by del ct, and this portion is nabla t ti. This portion is this. So if we view the time and space portions of the equation separately, it kind of looks like a continuity equation, where if the energy is flowing out of a box, then energy density must decrease over time. Then therefore del t ti greater than 0 and del rho e divided by del ct greater than 0, because here energy is flowing out of a box. If the energy is flowing into the box, the energy density must increase over time. So del t ti less than 0 and del rho e divided by del ct greater than 0. So friends, here you see that energy is flowing into the box. To make this continuity equation make sense, we must set this expression equals to 0, so that energy can never be created or destroyed. It can only flow in and out. Energy flows in and out, which results in changes to the energy density. When we say that the divergence of the first row of energy momentum tensor is 0, so friends, our equations should be equals to 0. So this equations is called continuity equations. This equations is called continuity equation. Here x momentum, so in case of x momentum is called conserved. So friends, we see that first row is divergence. This is the first row, and this is the second row is also divergence. So second row is also divergence, and when it is divergence, that means del x del t x t divided by del ct plus del t xx divided by del x plus del t xy divided by del y plus del t xz divided by del z equals to 0, and x momentum is conserved. And if you see in case of this, I just remove this portion, you will see same way in case of xi, when energy flows when energy is flowing out of the box, out of a box, then del t xi greater than 0, divergence portion is greater than 0, and in here the box should be del ct, del ct, del y, and del z, and this is the box, and del t xi less than 0, and this is the box should be del ct, del x, del y, del z. So friends, when the energy is flowing out the box, then energy density must decrease. Energy density must decrease, and when energy is outside, or when energy is flowing into the box, the energy density is must increase. You will see the same fact in case of second row. So we get a continuity equations in here. Basically, x momentum is following out of a time yz box, and then the x momentum density must be decreasing. So you will see the box is yz in case of x momentum. In case of x momentum, the box is yz. And so friends, we get a similarly we get another equations, that del t yt. So friends, you see that yz momentum also. This is the y momentum, and x momentum, y momentum, z momentum. So we can represent as the Einstein summation. These four equations can be represented in the Einstein summation conventions. So first equations can be represented. This is the first equations. It can be represented this way: del nu t nu, and second equation is del nu capital T y nu, del nu capital T, sorry, this is the y nu, not this is x nu, y nu equals to del nu T z nu. And for Einstein summation, we can then summarize all four equations as a single summation, where we allow the first index mu of the energy momentum tensor to be any of the four space-time indices. So divergence of a tensor del mu t mu nu equals to 0. It can be represented del t equals to 0. We are taking the divergence of a tensor. Divergence of each row equals to 0. For now, assume special relativity with Cartesian coordinates del E mu divided by del x nu equals to 0. That implies gamma del mu nu equals to 0. All coordinate systems, so for all coordinate system, del E sigma t is equal to del E bar sigma t mu nu E bar mu and E bar nu del E bar sigma into E bar mu plus, just we are doing covariant derivatives, t mu nu del E bar sigma E bar mu cross E bar nu plus nabla E sigma E bar mu. So friends, we just using the covariant derivatives, we must use a correct covariant derivative and take the derivative of the basis vector as well. Nabla gamma t mu nu equals to t mu nu comma gamma equals to 0. Summation using the notation with nabla symbol or this notation with the semicolon symbol instead of partial derivative only. This is the proper law of conservation of force momentum that works in all coordinate system. General relativity, conservation, so in case of general relativity, conservation of energy momentum only applies locally at an infinitesimal point in large region of curved space-time. There is no law conservation of energy momentum. For example, in an expanding universe, the wavelengths of photons expanding, wavelengths of photon expand along with space redshifting them to lower energies. Energies is simply lost, higher energy to lower energy. Energy is simply lost in this case and is not conserved. Example of energy momentum tensor: the dust and perfect fluid. Dust is the collection of particles not exerting pressure on each other. Each particle has 4 momentum p, densities described by number flux 4 vector n. Total 4 momentum in unit del x, del y and del z box t alpha t equals to p nt equals tends to pt, nt, px, nt, py, nt, and pz, nt. Speech: a unit xyz cube at some constant time, we just multiply p by the number particle density, which is the time component of n. Since p is the force momentum of each particle and nt is the number of particles in a unit xyz box, then p times nt will give us the total force momentum inside the unit xyz box, and which are the alpha t components of the energy momentum tensor. If we want to know what the force momentum flux in the x direction is, this is the force momentum contained in each unit time yz cube at a constant x and y. We get this by multiplying force momentum p by x flux, which is the x component. So friends, our diagram should be changed. In case of force momentum, x momentum, it should be ct, and it should be y, and it should be z, and this is the x for x momentum box. This box is x momentum box. I hope you can understand. And t alpha x equals to p nx tends to pt nx px nx py nx pz nx. Same as this is the nt. You will see this kind, but it is t direction, momentum flux in t direction. So this is the nt, and x direction, this is the this way. Similarly, we can get also beta directions, flux of force momentum in beta directions. We just multiply the force momentum vector by the beta component of the number flux force vector. So friends, you just see the t alpha beta can be represented in this way. t beta, alpha beta is the alpha beta, t similarly I can express is x and y and z. So friends, you can write t dust is equal to outer product of p and capital N. So how can you can get it is the, you can write this way. This is the row nt nx ny nz, and this way you can write that pt px py and pz. That implies nt pt nt px nt py nt pz, nx pt, nx px, nx py, and nx pz, ny pt, ny px, ny py, and ny pz, nz pt, nz px, nz py, and nz pz. You can write this way. In terms of array, the dust energy momentum tensor is the outer product of four momentum and the number of flux four vector using more abstract tensor. The energy momentum tensor for dust is just the tensor product of the four momentum and the number of four flux vector. This helps. So energy T dust, I can write T dust equals to P cross N, means the product of four momentum and number flux four vector. The energy momentum tensor is rank 2 and needs two transformation matrices. This is the rank 2 energy momentum tensor. EMT is rank 2. Now T mu nu dust equals to P mu in mu. This is the rank 2 tensor, tends to T mu nu lambda mu p and lambda sigma nu equals to T rho sigma is equal to transformation. This lambda p mu and lambda sigma nu is transformation. One for each index. When we change coordinates, one matrices change the components of the momentum vector. The other matrix changes the space-time orientation of the unit box. We use to compute momentum density. The energy momentum tensor itself is invariant. So energy momentum tensor itself and T mu nu lambda mu rho lambda sigma nu equals to T tilde rho sigma. Invariant, agreed on by all coordinate system. Invariant, agreed by the. So friends, we see that energy momentum tensor is invariant in all coordinate systems. Now T mu, now you will see this is the equations. T is equal to this is the energy momentum tensors. This is the invariant. Now I will discuss the transformations. P mu lambda p mu is equal to p tilde tilde p tilde p. How? Because this is the et ex and this dimension, and this is the p is the vector, and similarly you will see that et tilde x and et tilde t also same vector is p, and similarly you will see that transformation n gamma lambda gamma sigma is equal to n tilde sigma. This is the transformation, how it is n gamma gamma. This is the dummy index and how the changing with the diagram. Now t dust is equal to outer product of p and n, and you will see that n m ut ux uy uz and dimension, it is the multiplication utt utx uty utyz uz utxx utx or y u2xz yx utyy and this is the rho is equals to the mass density city is equal to mn. Tensor product of four momentum and number flux four vectors, we get the matrix times rest mass density. In this is the case of special theorem of relativity, and rest frame nc and mc, and perfect fluid. What is the perfect fluid? Perfect fluid is the particle exert the pressures p equally in all directions. Perfect fluid em tensor is energy momentum tensors. So first, perfect fluid energy momentum tensor is rho c square pressure p and all time, and another is 0. So friends, I hope I can clear something portions, and I am trying to discuss elaborately energy momentum tensors, but it needs a lot of discussions, because this is a very few discussions. We need a lot of examples and we have to practice a lot of facts. So friends, I hope you like my videos. Thanks for watching.